Hello, good afternoon to all of you. It's my great pleasure to introduce the third speaker of today, again from the Institute of Natural Sciences in Shanghai Yaoyu Tong University. I was lucky enough last September, I think we were running this workshop at FAU Fudan in Shanghai, and then I had the opportunity to visit for a couple of days Shanghai Yaoyu Tong, which is not that far from Fudan in Shanghai, and where I know Professor Xi Jin for many years now. And then I was introduced to Professor Nana Liu. She delivered a colloquium this morning, and also Professor Yaoyu Zhang. Yaoyu got his master and PhD in Shanghai Yaoyu Tong in 2016. Then he, as a postdoc, he was spending time in New York University, Abu Dhabi, the Quran Institute in Manhattan, New York University, and also Princeton. He's an expert in computational neurosciences and also on the theoretical mathematical theory of neural networks and learning and machine learning. And well, talking with him, I have the feeling that he knows many, many things that will be very, very useful for us in order to get deeper into the foundations of the mathematical theory of machine learning and also the neuroscience inspiration. And he was kind enough to be ready to spend here almost 2 weeks and in particular deliver this series of 5 lectures, right, starting today. So we will have 2 hours per day starting today. Well, not tomorrow and Sunday, okay? So you can still come if you want, but there will not be lectures, but we will continue next Monday. You have to check every day on the web in which room we are lecturing. I'm not sure it's going to be every day here. But in principle, this series of lectures will be recorded, no? Are they being streamlined? Yeah, okay. So one can follow them by streaming, and many colleagues are doing that, but also they will be recorded and hopefully will be a material of use also for future researchers willing to enter into this topic. So, well, he will now present what...
Yeah, so thanks a lot for the invitation from Eric. And it's my great pleasure to come here. And particularly, this is also the first time just to deliver this 10-hour kind of lecture series, particularly focusing on the progress I and my collaborators have made over the past actually 7 years, focusing on the kind of foundation of deep learning. And the goal is to give you a feeling that the deep neural network is no longer a black box. So I think probably because all of you do like math, and we are used to the case where whatever the problem we look into, we have some kind of framework to understand the problem. And then we never say, okay, anything is a black box. Like PDE can be very, very difficult. However, we don't say PDE is a black box or any difficult PDEs are like that kind of black box. However, for the deep learning, it's very different. And so we often say that it's a black box, despite the fact that its mathematical formulation, it's very, very clear. It's unlike our brain, where if I ask you to write down a model that tells you what happens in the brain or mimics our brain, that's extremely difficult. For example, maybe some of you know the Blue Brain project at EU, which is actually trying to kind of have an in silico kind of a model for our brain, or actually not our brain, but for the mouse. And so it does not really work as we thought. So we don't really have a good model. However, for deep learning, the situation is different. The model is just transparent, and we know every details. And when you train a network, you can trace whatever the intermediate kind of steps as you want. However, still, we use the word black box. that is a kind of a weird situation. So, of course, there's a lot of applications of current deep learning, and probably lots of you work on AI for science or AI for PDEs, and you may find the following fact: whenever you use in your algorithm, there's a certain part you use deep learning, and it's almost impossible for you to write down rigorous theoretical proofs that can really guide your kind of a practical, guide your practice. So in certain sense, it's really a black box in our kind of a whole kind of theoretical framework. And till now, it's still kind of difficult, but after all these 5 times of lectures, I hope you get a feeling that we already know enough that we can say we do have part of the answer about how that works and why it is so powerful, though this kind of a whole pursuit, this direction, is still at the beginning. And but later, in the next like 5 to 10 years, we are really expecting kind of a much better understanding in these directions, or kind of a better mathematical foundation or framework that emerged due to all this development. And all this, there's a kind of 5 lectures. The first, I just talk about some general situations of the deep learning theory. And the next Monday, I will talk about a particular important phenomenon for the AI for science that is called frequency principle or spectral bias. And for the later 3 lectures, I will talk about condensation because it's really a rich phenomenon. I've just give you a little bit sense of what is condensation in during the workshop. However, there's more details we can say about the condensation phenomenon. Okay, and so let's start. And I really welcome the interactions. Because I don't know how much you know about these topics, and if you have any questions, you just ask. So that makes these 2 hours like easier, right? And I hope to stop in the middle somewhere, and maybe Ziqi will remind me about the time. So it's, we don't like just go through this whole 2 hours. Okay, so first of all, this part about unimaginable achievements of AI. Just think about you are in a time of like maybe 15 years ago. And at that time, of course, all these achievements have not happened. And at that time, if people tell you, okay, we have methods to do all these things, can you really believe it? With all your theoretical understandings till now, but if I send you back to 2010, can you really persuade other people that all these things will be achieved? Okay, let's see what are the achievements. First, it's image recognition. So you know that Fei-Fei Li have invented this ImageNet, a very large data set with at least 1,000 different categories and over 1 million high-quality images. And you can see the neural network later, starting from 2012, the neural network becomes the only method that tops the rank. And you can see all these like 2010, 2011, these methods are not neural network methods. However, you can see starting from the AlexNet, so starting from 2012, you see the margin. It's like 10% margin. And it's just a starting point, this 10%. And later, quickly, it drops to this even better than this human performance zone. Because some of these things, particularly like a different category of mushrooms, even for human beings, it is still not so easy. But the neural network actually do these tasks easier than human beings. But there are some tasks that human beings can do better, but not these deep neural networks. But overall performance, so it is at the superhuman level. And then we kind of, in a time where we drop all these conventional methods based on like a handcrafted things. And if I ask you the question, is it possible like at a later time we will drop all these kind of learning-based stuff and there will be a super algorithm that will replace this kind of learning-based stuff? Is it possible? Yeah, if you really have a better answer to that, that means you see the future. Yeah, but my answer is no. If you really look at how the AI develops throughout the years, so these handcrafted stuff are something we really start with and we really like them. However, no matter how we like these handcrafted systems, they are just like very, very difficult to improve its performance. Therefore, you see very, very tiny progress. You probably get huge grant if you claim to make like 1% improvement, huge grant. However, the neural network easily gets like over 10% improvement on these problems. And it is starting from this problem that people realize that the neural network is not a method like only very few people can make it use on some problems where other methods can also do it well, like handwriting digits. If we use other methods like kernel method, it can also achieve like 99% accuracy with certain tuning. But it is from this problem that the neural networks stand out as the only algorithm that could top this rank. Okay, so therefore, before that, no one really expected that. Even people like Hinton, he has strong belief, right? But still, he cannot persuade other people. And then, that's the second part about Go playing. I remember the time when I was a kid, I read a book, okay, what are the difficult problems that for this AI system to solve? They said, okay, the Go, right, is probably the most difficult game that you could ever imagine. And I'm not sure how many of you have tried Go or know something about Go. I see some of you, right? Probably this picture will help you a little bit. Like, it's really about this kind of stones of different colors, and once certain stones are kind of fully encapsulated by the other color, and they got removed. So the rule is very simple. However, the situations are kind of exponential depending on the number of all these cross points, right? And there's a saying that, okay, the possibilities of Go is more than the number of atoms in our universe. In that sense, you cannot really do exhaustive search to find the answer to this problem. And therefore, in mathematics, people also talk about, oh, it's a kind of the search method can never really work for these kind of problems. However, from 2017, the AlphaGo just beat this world champion. And before that, the best Go playing system cannot even beat proper amateur kind of players. However, at that time, 2017, they beat the world champion. So it's really amazing. And when I go to the Institute for Advanced Study, and then at that time, like they told me, like Google give them lots of money. So, but you know, the Institute for Advanced Study is for like pure studies, right? In which sense they really get a touch on this deep learning stuff or field that is really like important. So, and Peter Sanak told me that it is from the success of Go, right? It's from the success of Go, he's a very pure mathematician. He has a strong feeling that it really has something, right? It's not kind of noise or anything like that. There must be something inside that, and probably we should understand what is inside. Okay, so that is the importance of these Go-playing systems. And how it works, so actually, if you look at the mathematical part, it's surprisingly simple. In a sense that what you do is like you give the kind of a current status on this board, and then you use that status as an input, and you ask the neural network to fit a function that tells you what is the action, what are the possible actions we probably should put our stone on. And then there's another part which is also a neural network. The other part is used to fit the value function, where at each situation, they will return a probability of winning. And then through this kind of a playing process, particularly from the AlphaGo 0, they use no human knowledge, just based on the rules, and they kind of play with itself. And then they learned these functions like excellent. At least these kind of conditional probability distribution or these value functions are far better than our brain. And that is amazing. But if you think of my problem, so I asked you to go back to 2010, and you know that this is possible. And how can you convince others that with the help of neural networks, okay, this can be done? If you just show them the mathematics, they will say, okay, I understand the mathematics, no problem. The first year with some probability knows what you are going to fit. However, why the neural networks can fit it well and to a kind of pro level. So that's really a problem. That's a Go playing. And this one, protein structure prediction. So this one, all of you know the news where like they got the Nobel Prize in chemistry in 2024. And sometimes I ask my students, so what surprises you with this Nobel Prize or this Nobel Prize winners? What surprises you? And anyone thinks that that kind of Nobel Prize winner will really surprise you? It's about the age. You see that it used to be the case where Nobel Prize winners are like getting older and older. It's not like at the time when these kind of quantum physics, you see the Nobel Prize winner at that time, like 20, 30, like it's, yeah, I'm already old at that time, right? So, however, in these, like in these few decades, like people like Higgs, really, I mean, he lived to the time where Higgs boson are kind of got verified. And he's old enough, like over 90s, and get the Nobel Prize. Like we think that probably it's not a good time for our young people, because even though we do something good, and still we need to live long enough to see that becomes a prize, right? That is really discouraging, right? And however, you see these guys, like Jumper, is less than 40, right? And the time between his work and the prize is just several years, right? That is really amazing. And that is something happened in the era of AI. If there's no such new things, like no matter how clever you are, like you need to wait to a much older time. So that's really some good sign for all of you guys, meaning that the discoveries, the important discoveries, you may have a chance to make at a young age. Okay, that is protein structure prediction. And okay, what is it doing? And I'm not sure if some of you know that the protein folding problem actually is a very important computational mathematical problem. Particularly, it reminds me that at like 2010, like Professor Wei Nan Yi have, at that time, was doing on this real event and the string method, all this stuff. And they trying to find the transition paths between different local minimums or some states, and how the, for example, chemical reactions, how like different particles, like they will, from some initial state, changes to the later stage, and how that path goes. And that problem it's similar for the protein folding, where you have some initial configuration, and later, throughout certain kind of path, it folds into kind of minimum energy state. And the computational mathematicians are trying to coin methods for that, if we really find effective methods that later leads to the solution of this protein folding problem, then it could be that our applied mathematician win that prize, right? And that's really nice. However, what happened is that it is not that we can't do contributions. It is just that, so not enough people are sensitive to this new approach. Yeah, and I think applied mathematicians, or this mathematical community gets to notice this problem like probably since 2017 or 16, and it's a much later time. Okay, the method is as follows. So all this method forgot about all these seemingly like basic mathematical formulation of this problem. Okay, there's a string where we know something about its energy, and then it folds to the minimum energy state. It considers nothing of that. What it does is it asks the following question: just from the sequence, if two DNA sequence, they are similar, does this structure has a similarities? If so, that means from the mappings or from the limited kind of this sequence and the structure relation data, it's like 20,000. From that limited data, if the rest of this sequence, no matter, it can be unsynced sequence, but if there are similarities or some patterns, statistical patterns, that is inside this mapping, or some regularity inside this mapping, then we can use machine learning methods to capture that mapping directly without understanding how it is related to the energy, right? Okay, so that is the idea. Of course, to solve this problem, because the data is relatively limited comparison to, for example, image recognition or kind of language tasks, it's rather limited. It's like 20,000 with huge price paid to uncover that. Therefore, it must employ our prior knowledge about this sequence. And what it does is to have like a relatively clever kind of matching kind of part, which can give better encodings of this sequence, and then trying to match that sequence to a structure prediction. And I will skip all of the details, but just tell you, okay, this prize, it's a win from a completely different approach from computational mathematics. Therefore, whenever we think about some difficult problems, we should always keep that kind of approach in our mind. It is highly possible that some conventional approach is hopeless to find something. And we have actually lots of understanding about why we cannot solve the protein folding problem from the computational perspective. Okay, we say that this energy function has like exponentially many local minima, that it's hopeless to really explore these exponential many local minima to find the global one, right? We have all this understanding telling you that one road is not possible, so we give up. However, there are some round tool or some other strategies that really gets you to the end. So we must have an open mind to learn how to keep attention about all these, what has happened, and therefore maybe more problems that cannot be solved in the conventional way can be solved later in our time. That is our opportunity. And also, let's think about this image or video generation. How many of you have used this kind of, say, mid-journey or kind of stable diffusion? Yeah, I see many of them have used. I always feel that it's really amazing, right? It's really amazing the quality it generates. And so I don't know, even till now, I really have a hard time to believe that we could do that in this level. Because once I've asked students in that learning with a major in design, and says, okay, so how much I should pay you to generate a picture like this for me, right? They said like 5,000 yuan, so probably it's like 700 euro. So it's just to generate, but now it's just one click. You get that, right? And also about video generation. So this is yeah, it's like that time. Particularly, so the earlier generation using GAN. However, the GAN still cannot do all this generation to that kind of quality. And it is since the development of the diffusion models that we get things like this quality. And let's look at this Sora, right? The Sora stuff. So can you really imagine that this is possible? It's not filmed by people, right? It is generated from an AI. So I'm not sure if some of you know about this photography or this video recording. Is it difficult? Because I see you must need a drone to kind of like do this kind of stuff. It is not really like it's not really like it's easy to do, right? However, now these things can be generated by AI. And it used to be a case where you need to master lots of different techniques in order to kind of have this kind of degree of freedom regarding this kind of angles of and how these things, the translation of these things. Yeah, but now the AI gives you far more degrees of freedom to deal with this kind of stuff. It's amazing. And what about this one? Yeah, it is. Okay, so let me ask you the following question. Do you think the generation of this kind of stuff, it's a kind of, you think it's really a positive or negative regarding this? You think that's, okay, first, it's amazing it can do that, okay? The second is that, okay, it's not physical at all. Okay, it's really bad for this kind of technology. What do you feel? Positive. So what do you think? Not physical, right? In the sense, for example, if this happens, then this glass should break, right? But that does not happen. And of course, it's a kind of a reverse process, right? Because we know that it's not reversible, essentially, this kind of process. But it generates a kind of a reverse process. Therefore, it's also not physical. Yeah, and how many of you think it's, oh, it's really nice to see? How many of you, okay, it doomed this technology? Well, it's still some of you, okay. But let me tell you the following. Whenever a new technology comes, it's easy to say, okay, there's lots of bad things about that. It's so easy to say that. So what is non-trivial is that despite these kind of limitations, you see there's something that have never been done or can never be done before. For example, let me ask the following question. In your dream, does your dream follow the physical rules? Really? No? Yes or no? Not really, right? So, but you see, if you think that it has the capability, just like your dream, to generate vivid kind of videos, and you can see that is amazing capability, right? The physical rules I can tell you that even our brain cannot really generate things that follows the rules. It is after learning something, and then externally, this kind of knowledge help your imagination. It's not that your kind of instinct can generate things that follow the rules, right? So it reached a level of human kind of generation capability, right? Yeah. So like LeQuinn is always saying, okay, it's not physical, but I think he missed the main point of this kind of technology. Okay. So the technology behind is called diffusion model. It's actually, from the mathematical point of view, it's really simple. However, it is very, very effective. So the what diffusion model do is that we have tons of image, and we can add noise, so that as long as you add enough noise, the distribution of the image becomes Gaussian, right? And then if you want to reverse a process, for example, you give a Gaussian noise, you want to generate a picture from that, or sample a real picture from that Gaussian noise, right? You can think of this problem mathematically or from the computational mathematical viewpoint. How can you sample a random natural image? Can you really do that? You can sample a random the noise from Gaussian distribution, but how can you sample a random natural image? We have no capability of doing that. We don't understand how this distribution looks like. We don't have any mathematical formulation for that. We do understand a little bit about how the statistics of the natural image, for example, it decays in the Fourier domain. However, apart from that, we have no way to sample a random natural image. However, now we have that capability. And that capability is realized through using the neural networks. You can see, okay, there's a mathematical process that is ongoing, and you can write it down in 2010, no problem. However, if without neural network, can you really realize this process to that extent? Okay, I bet no. Okay, and now there comes the large language model. So it is really a milestone towards the, maybe some of you heard the notes of AGI, right? It's I want to know how many of you think that the current large language model achieves, to some extent, the AGI. The AGI stands for Artificial General Intelligence. Yeah, you can interpret general in your understanding. Like, how many of you think we already achieved the Artificial General Intelligence? Raise your hand. Oh, very few. So most of you do not think it's a... But if I say it's a milestone towards AGI, how many of you disagree? No. That's a milestone, right? Okay. So you see, I sometimes find it silly to debate on whether this large language model is AGI or not. Yeah. It's the same thing, right? We use the same model, right? However, we keep debating whether it is AGI or not. It's like words, it's like definition. Like, for example, if there's nothing apart from our human brain that has some general intelligence, then how we define that kind of thing, right? It's a silly. So whatever. So it's a milestone in the sense that we used, for example, Google Translation. They used to be the champion in translation, right? But you cannot use it for like a Q&A, right? And then we have lots of other kind of machines that can do a certain level of Q&A. For example, it used to be the case when you call someone, there's a robot on the other side, right? And at the earlier time, it's a kind of expert system. It's not rely on this large language model. And now there's one model that do all these kind of language-based tasks to the top, right? And is it trained specifically for translation? The answer is no, right? If it is not specifically trained for translation, why it is currently the best method for translation? Why is that? right? It must have some generality. Means that even though it is not especially trained for this task, but still from all this learning, from learning other things, all these things help it to do better translation. So that is a generality means, right? So all it does is to do, we call next token prediction, right? We predict the conditional probability of the next token. And from that, so it's always when we come to this mathematical nature or mathematical formulation of that, we find it's surprisingly simple. It's not difficult at all. However, if I ask the following question, or you go back to 2010, you tell people, okay, as long as my machine can fit this probability, a conditional probability well, that machine can pass the Turing test. You see, that's just a mathematical argument, right? I did not say, you say whether this can be done or not. I just ask you if the machine can fit this conditional probability well. Can it pass the Turing test? I don't think you have any mind, right? People have any mind about this. Even till now, it's still difficult to imagine, but we are getting used to that. Okay, so it's our generation getting used to all these kind of achievements. Okay, and then now let's just go to a little bit kind of a mathematical stuff, and you can feel the difference. Okay, on the previous slide, I tell about fancy achievements, right? That's really fancy, that's amazing. But now we brought down all these things to its kind of formulation. And then if I ask all these AI achievements, what serves as the engine for that? You know, if you have a car, then you must have good engine, right? We used to have like steam engine, but now there's kind of much better engine that support the performance of that car. And for AI, if we can do something that has never been done before, what is the engine for that? What engine made it possible? The answer is deep learning, right? So what is deep learning? So simply says that deep learning is you use certain model. That model, later I will tell you, but it's a kind of, if you use this kind of neural network model, right? And then put this model in this kind of empirical risk minimization problem. So this empirical risk says nothing but just if you get in samples, like for example, 1 million image, and then you ask this neural network to predict the category of this image and compare to its ground truth, y. And then initially it does things terribly. But later, as you minimize these theta through gradient-based training, like it can be like gradient descent or stochastic gradient or ADAM or this gradient-based method, and then later this neural network can learn all these in samples very well if you use a big enough neural network. And then, as long as it learns this empirical risk to some global minimizer, or close to that, then that model can have all these kind of amazing capabilities, right? All these things we have seen before. It's nothing but this simple minimization procedure. And if you ask people which part of this mathematical formulation not known at 2010, the answer is everything is known at that time. Yeah. Therefore, if you go back, you first tell you, okay, do you believe all these achievements can be done? Probably many of them says, oh, no, it's unimaginable. However, if you tell them, okay, I'm come from the future, and this indeed has been done, and then they ask you, what is a mathematical formulation, how that algorithm looks, you show them this one. And then they said, just this? I can't believe, right? But you know, that's indeed, there's nothing more than that, right? And there's more you can feel that if once you change this model to a linear model, we know everything. We know everything since very, very early. If this one is a kind of linear model, no matter over-parameterized or not, we know fully about how it evolves and what kind of solution it learns, and there's no mystery to that. However, as long as we change this model to some neural network, some specific family of non-linearly parameterized model, it becomes a superb engine for AI, right? So it's just that change. The model change, we change the model from this linear model to this neural network model. And then, so lots of magic. It becomes a very, very powerful thing. Okay, and so the left part is the deep neural network, and later you see all these achievements, and we are in these questions. And why is that? Because we don't have a framework to help us understand these mathematical formulation, particularly that neural network model, the relation between that neural network model and the superb or unprecedented performance of that thing. Okay, so sometimes we use the words of black technology. Have you ever heard of these words, black technology? Yeah, I learned that from Japanese cartoon. So that means a technology that we don't understand, but we already have, right? There's some cartoon where it says that there's some leakage from the future that gives you some technology, but not the science, right? So you got this, for example, AI, got all this kind of spaceship. However, you can build that, but you don't understand why, right? That is called black technology. So let me ask the following questions. Which of the following you think are the black technology? So let me ask first, the synthetic diamond. You know that now we can kind of, there's a kind of a trend, particularly in China, so we can do the synthetic diamond, right? And from the carbon. And do you think that's black technology? No? Yeah, I think most of you. But what about like 200 years ago? Yeah. I think definitely that's black technology. Why is that? So because the carbon or graphite are so different from diamond, right? There's no way you see the one thing can be turned into another. You may feel that made gold from copper makes more sense because they have similar colors, right? However, not the graphite to the diamond. But later, we know the elements, and then we can predict about this. We have some sense, okay, because they are all carbon, therefore one thing can be turned into another. Okay, the second is atomic bomb. Is it black technology? Yeah, no, right? Because from the Einstein's equation, right, we know that the mass can be converted into energy, right? We just need to find the right element to do that, and all these engineering efforts. And also about Apollo program, right? We land the moon. Is it black technology? I think probably no, but I don't know from the control viewpoint, is control, this kind of theory, good enough at that time to say it's possible? Probably yes, right? Yeah, but yeah, if yes, then we kind of anticipate that, right? It's just engineering. But ChatGPT, right? Can anyone predict the birth of ChatGPT at the time of GPT-2 or GPT-3? I think very few of you, because otherwise probably you can do something. You can invest, right, if there's any way. You just join them, right? At that time, it should be much easier to join them, right? So you see that's black technology. And the quantum computer. Yeah, Nana, what's your idea? If it comes, if we later have the quantum computer. Yeah. Yeah, we currently have some framework about this quantum computer, right? A quantum computer that accelerates AI. Probably that could be a, I see. And the last case, it's like a 0.1 light speed spaceship. If that happens. Kind of in between, right? First of all, we did not say that it's a kind of light speed spaceship, right? It's a kind of possible. However, we really don't understand how it is possible from other perspectives. Okay, so now you have a sense in which sense there's something are black, in which sense something are not, right? It is the theoretical understanding, right? If we have some theoretical understanding of the system that help us predict the performance of certain things or capability of certain algorithms, and then that is not black. However, now, because we still don't have a very good theoretical framework for AI, therefore, even till now, we see the ChatGPT, but it remains black technology. Yeah, but we hope that like 5 to 10 years later, it's no longer black. That is a progress of science. Okay, so probably shall we kind of break for a while, or you feel it's okay? Because it's just the stories, right? Now it's nothing really kind of make you bored. So, okay, now let's go to the beta lesson for deep learning theory. I sent that famous paper. It's by Richard Sutton. How many people know about Sutton? Because like he just won the Turing Prize, right? Turing Prize this year. So it's said the father of the reinforcement learning. And there's a very famous kind of blog. He wrote that blog. It's called the beta lesson. And he says that the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective, and by a large margin. And therefore, the information from that lesson is that we should design algorithms that leverage computation or this learning capability instead of human knowledge. So that is a key. So if you read that blog, then you can see that we have a tendency to rely on our human knowledge, right? Because we can do something. And then we try to extract how we are doing these kind of stuff. For example, Go playing. We try to extract from some pro game Go player, so how we do things. However, that kind of strategy in the history does not work for AI, does not lead us to a better AI. Okay, so you see what's interesting is that before he win this Turing Prize, I kind of chat with him in a conference. So I asked him, how bitter is this beta lesson? He said, quite bitter. Yeah. So it means that at his young age, he really kind of are fans of these algorithms, elegant algorithms based on human knowledge. He's a big fan. However, it is with all these years of frustration or failures that he learned, and he tell it to everyone else. Right? We must leverage computation. So in theory, in the deep learning theory, is there any such lesson we should learn? If we must learn something, can we learn it from an earlier time? Not like 20 years later, like, right? Because this kind of beta lesson is learned by the facts. Because already there are 2 lines of research and one line beats another. We see the ending of that story, and then we learn that lesson. But what about deep learning theory? Is it possible to learn some lessons at an earlier time, at the time where we are still on the way to that, and so that we can avoid that the beta lesson is not so bitter when we really finish that task? So that is what I'm going to say about the deep learning theory. But first, let me tell you about the timeline of neural network development. I think probably some of you have seen that. So we used to characterize the development of AI with this spring, or someone called it golden age, and also this dark age, or we call it the winter time. So you see that in 1960s, there's a spring where you can easily get funding for that, and people are just sometimes too optimistic about this, the power of AI. So that comes to a spring. However, from this 1969, this book about the perception by Marvin Minsky and Popper. And then it says, okay, the neural network, the one neuron network cannot even solve this exclusive OR problem. I will later tell you about that. And then, of course, at that time, he actually, there's a theory in this. The theory says, okay, one neuron is limited, but with a neural network of multiple layers that can be solved. However, at that time, we don't have proper algorithms to really train the multi-layer. They know that the multi-layer neural network at that time can express this more complicated target. However, we don't have training algorithm. Then that leads to the winter. It's not that he said anything incorrect theoretically. However, it's just the implication from that make people kind of pessimistic about the future of AI. That leads to the winter. And when the next spring comes, actually it's not till 1986, it is actually from the Hopfield. So who got the Nobel Prize in Physics with Hinton, right? So what is the contribution of Hopfield? Many people actually, particularly AI people, feel it's not proper to give the prize to Hopfield because Hopfield network is not used in current AI. Right? We don't really use that. So, but what's the real contribution of Hopfield in AI? Because he leads to the second spring. And it is after his work that more and more people get optimistic, get optimism about that, and that leads to the second spring. And during that spring, and the particularly important thing is about the backpropagation. So why the backpropagation is a big thing? Because previously, what we use this activation, Heaviside-like activation. So this activation has zero gradient almost everywhere. Therefore, you can never use gradient-based training algorithm for these kind of activations. However, at that time, people realized that we can just use more smooth, for example, sigmoid activation. Therefore, it's just, we can directly use gradient descent, right, to train the system. And then that leads to the backpropagation. And at that time, you can see all these basic elements I present in the earlier slide actually is already there. So that's a landmark because all these necessary components of this for the mathematical framework is already there. So, and there's a second spring. And there's also like this universal approximation theorems proved during that time. And later, there's another winter. And so I think I will skip some details about this winter and the spring. But to just tell you about the last part, about 2006, many people may know that in 2006, there's a paper, I forgot the Nature of Science paper, by Hinton. That is about how to use the restricted Boltzmann machine to pre-train the network to get a good initialization. So that is about that. Because at that time, before that, so the initialization, people know that, or particularly like people like LeCun, they can tune the network so that the performance can achieve state-of-the-art on all possible tasks, but not other people. Why is that? It seems that they don't understand how to initialize or how to tune these hyperparameters. Therefore, at that time, the Hinton tries to get a more systematic the method to give the network a good initialization. Therefore, what he used is to use restricted Boltzmann machine to initialize the network. However, that later are fully abandoned because we know that that is not necessary. We just need to initialize with proper variance. Later, I will tell you how that variance kind of changed the dynamics of the whole network. That is about the condensation phenomenon. But the 2006 later leads to the spring. So not based on its real contribution to the later development of AI, but it makes people optimistic about the ability to train the neural network, deep neural network. Okay, so that's the general stuff. And if we particularly focus on the deep learning theory, what are the kind of key events? The first of all is the book of perceptions, which tells the limitation of like a one neural network, but also tells you, okay, so multiple layers of neural networks is good at approximation. However, we don't have good training algorithms because the neurons at that time has heaviside activation. Okay, and then to 1986, the backpropagation, that leads to the emergence of modern deep learning framework or formulation. And then 89, universal approximation theorem, and 95, there's a generalization puzzle proposed by Leo Breeman. And still, this puzzle, it kind of drives the community till now. And also, there's a Vapnik-Jekyll bet witnessed by Yan LeQuinn about whether we can develop a deep learning theory in 5 years. Definitely, you see, we failed to do that at 2000. And even till now, so still, I mean, we are ongoing. And at 2017, there's a huge gap. And then the generalization puzzle got demonstrated in these more SOTA settings with large models and the data set. And 2018, the neurotangent kernel stuff, which leads to a surge in deep learning theory research, because a lot of people working on statistical learning theory can their kind of approach can be used to analyze the neural network in this neurotangent kernel regime. And I also put our results about frequency principle and spectral bias. The spectral bias, it's, the name is from the Yusha Benjo's group, and we call it frequency principle. And this is particularly used in the area of AI for science, because in AI for science, we do encounter like high frequencies in a variety of problems. If you do not realize the frequency principle, you can easily feel, okay, the neural network is just so bad, it cannot be used. But if you properly tune this network or well design that based on the understanding of frequency principle, actually we can deal with these high frequencies. Okay, and this line will stop there, but the conclusion is despite 40 years of effort, framework for its math foundation yet to emerge. Yeah, and but this 30 years, is it long enough for us to learn something, to learn a bitter lesson? Okay, so let's look at this Vapnik-Jekyll bet in 1995. You see there's LeQuinn is here. The Vapnik, I think probably many of you know, it's a kind of it's a leading expert in statistical learning theory. And like VC dimension, like it's this Vapnik. And Jekyll is at the time the leader of the team where it's LeQuinn is in, right? At the time, he's a kind of leader of the LeQuinn. And then they kind of bet a fancy dinner that by March the 14th, 2000, people will understand quantitatively why big neural networks working on large data sets are not so bad. Understanding means that there will be clear conditions and bounds. Vapnik bets one fancy dinner that Jekyll is wrong. Yeah, you can see. Yeah, they are, yes. So you see that some are very optimistic about that, and yeah, some are pessimistic. But the fact is, even till now, right, there's no winner in that. And what's the current situation? Yeah, still that go back to the notion of black box. And you see that is from the 2017, but still it's good enough to capture how we feel, the general feeling about the deep learning. It says that no one really knows how the most advanced algorithms do what they do. That could be a problem. That could also be a problem today because the theoretical foundation is not yet ready. And there are famous cartoons that describes the situation of AI. So if we do not make that much progress in 40 years of effort, then there must be some reason. And these cartoons tells you some of these reasons. That is from the Donahoe's PPT. But actually, you can see from Donahoe himself's work, he cannot really avoid these kind of traps. Yeah, but you see that is, so the police said, this is where you lost your wallet. The man says, no, I lost it in the park, but this is where the light is. Yeah, so how can you find the key, right? That's not possible. Okay, there's another cartoon that actually I would feel better captures what we are doing now. So deep learning as a magic mirror. So every theorist who looks at it see what they wish. Yeah. You can see that there are people from different disciplines or different subjects, they work on AI from different perspectives. However, yeah, you can see, first of all, they don't necessarily communicate that much. The second, they all seem to make some progress. Yeah, and sees what they wish, because it's a complicated enough system. There's always rooms to look at from a different angle to say something without touching the essence of that. Yeah. So therefore, though you see a bunch of papers, still the situation is that the foundation is not yet ready. Okay. Now that comes to my personal view about the bitter lesson in deep learning theory. So I would say that all previously existing frameworks, irrespective of their origin or demonstrated success, are ineffective for understanding deep learning. So that is a lesson I learned through all these 40 years of exploration. I see how that evolves. However, that conclusion are just so persistent. And what are these existing frameworks that people adopt to analyze deep learning? Just to name a few. For example, the most prominent one is statistical learning theory. It is the main community that kind of work on deep learning theory. And second is, of course, numerical analysis. Yeah, I just say frankly, numerical analysis, there's a framework to understand things, right? We try to understand the function space and then try to understand these arrows, right? We use the name of arrows, different kind of arrows about that. And also, we emphasize on the curse of dimensionality. Yeah, but whether that kind of emphasis really helps you understand the deep learning, that's a question. Definitely, numerically, we care about curse of dimensionality, but whether that is the essence for deep learning method, that's a problem. And also statistical physics, Nana is here. He is, yeah, but a lot of, actually, there's a long tradition that statistical physicists are interested in these systems. Yeah, however, they didn't make much contribution to this problem. And also statistics optimization community, and also neuroscience or psychology community. Yeah, so someone said, okay, we need to borrow the methods from the neuroscience or even psychology to understand this system. Yeah, so maybe a lot of, and also someone we also say like kind of more fancy mathematical framework, maybe like category theory or that to understand this kind of stuff. But if you buy my lesson, the bitter lesson is whatever they adopt, as long as it is not the framework for deep learning, right? It is framework from other place, then they are ineffective for understanding deep learning. So that is the general conclusion. Yeah, so that explains why it is so difficult. Constantly, you see, particularly our time, there are some new people coming into this area. However, if they do not really hear this beta lesson, after several years, they will find that no contribution has really been made. The theoretical foundation is still not emerged. Okay. So, and I would say existing frameworks often misleads, right? Particularly regarding the importance of different things. Okay, existing framework tells you, okay, something is important, but actually probably that's not true. So the cartoon is like, we say, it's why existing frameworks misleads. It's like the blind man that tries to understand the elephant. They've never seen elephant. Yeah, whenever they see certain part of that, they always kind of interpret that with their very strong bias. Therefore, you can see that they kind of get different kind of parts of the same problem. However, they too quickly arrive at a conclusion which does not really reflect the object itself. And you can see that everyone must keep that in our mind, that deep learning is a completely new object that have never been seen before or have never been understood before. It could be a completely new species. And in face of that species, all of us are blind men. It's not that we are blind, it's not. But we must have the attitude that we are blind. Therefore, for everything we touch, for every phenomenon we observe, we must be very careful about what we can say about that, right? We must keep a clear mind that we are blind men. We only touch certain aspect of that problem, and we must get like more information. Okay, and then now that goes a phenomenological methodology I actually advocate for a blind man, because as long as you admit that all of us are blind men, so what exactly we can do in this situation, right? First is suspension. We must suspend the priors and belief one may hold and focus on the facts about the objects. For example, if you touch the tail of the elephant, you can't say it's a rope, but you can describe the thin, long stuff, right, that is there. And therefore, so we must suspend all these kind of values or the understandings of the importance. For example, in some of these, for example, snakes, right? If you touch this kind of a nose, right? Oh, it's a snake there, therefore I see the whole stuff, right? But that's not true, that's more misleading. But we can always focus on the facts. We touch on certain part and then we describe it faithfully. And the second thing is accumulation. So discover and accumulate all possible facts about the object and prioritize the more informative ones. So since we are blind men, we only see part of that. We must collect the information from different angles. That, as long as we collect, as long as we kind of discover more and more aspects, right? Particularly, for example, for the elephant, if all the facts you have is about its nose and its tail, there's no way you are going to have a good understanding of the elephant in a whole, right? Therefore, in a stage, we must accumulate more facts about this stuff. And the third stage is, as long as we get sufficient progress, we get more and more. For example, for the elephant, we have understanding of the nose and tails and also its legs and its body. And then a new framework shall emerge once all these enough pieces are uncovered. Where we are now, we're at this second stage. Yeah, why we don't really understand, or why this new framework has not been emerged, because some pieces are missing. There's some main part we have not yet uncovered. Therefore, it's not possible for us to really have a kind of holistic view of that stuff. Yeah, but later, if we collect enough one, we will be able to do that. Okay, so here's an illustration. You see, it's like a jigsaw puzzle. So first, the suspension. You can see that if you have strong prior, you can too easily try to piece up even tiny bit of pieces into a whole. You see, that's everything, right? But with suspension, you are required to make all this evidence into different factual pieces, right? If you did not get a good the view, okay, you don't know, maybe this piece is important, maybe this piece is not, but you cannot really judge which part is more important for this whole picture, right? And so you need to suspend all your values about this kind of different part, but focus on finding these new pieces. Okay, so that goes to the second stage. You just accumulate more and more facts about this jigsaw puzzle. And then once you got enough pieces, then there's something emerges from that. And that is the time you have a good framework that can help you. But if there's some key pieces that is missing, it's not possible to really understand it. Okay, so as long as I tell you the importance of accumulating the facts about this kind of stuff, and then there's a key family of facts, because most of you are mathematicians, you may feel that theorems are facts. That's definitely true, right? But there's a very important family of facts that is called observable facts, or that is with the name of phenomena. So the phenomena emphasize the thing that probably is not kind of a theorem that is proven strictly, but we can observe. I can tell you the condition, you can replicate my experiment, and you can see the same thing. But the description may be not in terms of mathematics, but you can observe, you can replicate my experiment. Yeah, for example, just as rainbows, right? There's a rainbows, but writing down the equation is not necessarily a good step, or it's a much later step than just describing there's rainbows that happens after rain, right? That kind of phenomena is really important family of facts we should uncover. And there are lots of things that we have some, we can accumulate many kind of phenomena throughout the years. And so, but does all these phenomena, or are all these phenomena important? Yeah, I would say not necessary, but if you are lucky enough to uncover a really central phenomena, for example, like this piece, and then it guides you to find some adjacent pieces. Just from the piece, this piece, you find, okay, there's something missing, you must find them. And then you put your time, maybe 2 years, to find all these new pieces, right? And these new pieces will guide you towards more missing pieces, right? And then, if you accumulate to this stage, there's a new picture emerges for this object. And if it is, for example, some of these phenomena may not be as good as this one. For example, if I just look at this corner piece, right? This corner piece may not really help you identify the neighboring pieces. Therefore, yeah, I think these years I'm really lucky to kind of uncover some of these key pieces where, based on this piece, we get lots of kind of important information about these phenomena. So later, we are at a much better position to have a framework. Yeah, I think we'll just stop it, to just rest for a while, and we can discuss, or you can go, and we will continue later. Yeah, I should use this. Okay, what are these basic facts we need to know about this system? First of all, it's a one neuron and its behavior. Okay, so neural networks or artificial neural networks are kind of made of this bunch of artificial neurons. And yeah, thank you. Artificial neurons. So what can one neuron do? So this problem has been well understood like years ago. So it cannot do much, but just to consider this is a fine transform, and then with a nonlinear activation. So what's special about this neuron? So first of all, some of you maybe know this Kolmogorov-Arnold representation theorem, right? So you see this activation function is a nonlinear function. However, it's a nonlinear function in single variable. Most of the time, we are dealing with functions with multivariable. But should we really considering using this nonlinear function with single variable to learn the class of functions with multiple variables? Yeah, but no matter the answer, so we do have this kind of mathematical basis, for example, Kolmogorov-Arnold representation theorem that tells you, okay, it is possible. It is like a two-layer neural networks with certain, not necessarily continuous activations, but we only need finite of them to represent a nonlinear function. But in current neural network, it seems that these kind of forms where the key nonlinearity happens with respect to functions with one variables, it just seems that this kind of representation is so important. But people are also thinking, is it possible we use some nonlinear activations regarding multiple variables, right? Is it change this kind of building blocks of the neural network to kind of multiple ones? Yeah, but nevertheless, we can think about that. Probably we can get some benefit of that, but still, I must tell you, okay, using these nonlinear activation functions with a single variable is a very important kind of characteristic of current artificial neural network. So you must keep that in mind. Okay, the second thing is, what does this kind of linear transform do? If we consider a very simple activation function like a Heaviside function, and then all it does is to cut this plane, the space of this X, into by a hyperplane into two parts. And one part is characterized by 0 and the other with output 1. So there's nothing else it does. Therefore, what can single neuron do is to kind of split this whole space into two parts. And that is good for the classification problem, which are linearly separable. And if the classification problem are linear separable, we can just use one neuron to do that. Okay, so that is definitely a problem you can do, right, with this 0, this black side 1, and just draw this one line. And therefore, you don't need to go to this formulation. Just look at this data, and you know that one neuron can do that. However, what about this problem? This problem is called exclusive OR problem, where you see that if it is kind of both of them are 0 and both x and y are 1, this leads to 0. And however, if they are opposite, that leads to 1. So this kind of exclusive OR problem is not linearly separable in this 2D space. Therefore, the prediction or the understanding is that you cannot use single neuron to do that. Of course, with two neurons, you can do that, or with deeper neural layers, you can do that. But single neuron, that's the boundary. It cannot really do this stuff with this like a Heaviside-like function. Okay, that's about the single neuron. Okay, very simple, right? There's we understand it just long ago since the starting of this artificial neural network. But the strange thing is that the understanding of single neuron does not really help us understand the behavior of multiple neurons, right? There seems to be a huge gap. That is usually the characteristic of complex systems. Whenever we see complex systems, for example, our brain, what we're seeing, sometimes we are saying that even though we understand each single neuron, its dynamics completely, still there's a huge gap from that kind of single neuron understanding to the understanding of the whole system. There's a huge gap. That is, someone will use this word like emergence. That actually means there's lots of properties of the network that cannot be predicted from the knowledge of single unit. In general, we are saying that. So this artificial neural network is definitely one of the complex systems. It's not as complex as our brain, but nevertheless, the single neuron understanding does not really help us understand this network of multiple neurons. Therefore, we should keep going. So I think there's nothing much to say. It's just a composition from the mathematical point of view. It's just the composition of different layers. At each layer, we can have multiple neurons. And that is the deep neural networks. And then that goes to the universal approximation theorem. As long as we have one hidden layer of neurons, and then we know that we can use this neural network to approximate any continuous function. Now, I ignore some of these conditions, like the support of that, to give you a sense to any desired precision. And the requirement at an earlier time is that the sigma z is kind of well-defined as z goes to -infinity or infinity, because some of these proofs relies on the rescaling of that the activation function. After rescaling, it can be a Heaviside function. And therefore, we can use the results of Heaviside function to construct this kind of compact basis kind of these kind of stuff. And then we can use that to do these, to finish these approximation results. But later, all that required is just a non-polynomial. So you just need this sigma to be non-polynomial, and that is sufficient to get this universal approximation. Okay, there's a sketch. I personally favor this kind of construction proof because it sometimes gives us a sense of how that approximation is possible. Yeah, and probably many of you know there's this kind of statement that tells you, okay, the space that it can, or the function it can express is actually dense in certain continuous function space, but that kind of dense argument often obscures the difficulty of representing certain difficult functions, right? How difficult is that? Usually that theorem does not really tell you. It is from the construction you have some ideas of what are the targets that are difficult to represent. So generally the proof is the construction proof is like we can construct like Heaviside function from the given transfer function, and then use that to construct bound function, just like what we consider in this kind of a finite element methods or tower function in 2D. And then we just approximate the target continuous function with these bounds or these tower functions. That is how we do. However, definitely from that you can see it's actually difficult, right? It's not easy. If I ask, can neural network really learn this kind of constructed approximation? Right? I think most of time you will see it's the neural network do not learn in that way. Yeah, but nevertheless, you can do this kind of construction proof, and you can say if you have some more clever construction, so that the neural network can actually tend to learn what you construct, right? Can you do that? Yeah, I think it could be very difficult. Yeah, but what you can do, you must have very good understanding of how neural network learn these targets, right? That kind of information is something you must have to think about these problems. You cannot just sit here and say, okay, how I'm going to approximate. That will never tell you how the neural network actually approximates things through training. Okay, there's a very important theorem, not specific to neural network, but very important. That is called no free lunch theorem. So the no free lunch theorem, I will not really kind of read all these sentences, just to give you an example. So what no free lunch theorem says, okay, I have this x1 and x2, two variable. Each of them takes 0 or 1, which is a discrete input space. And then I give you some of these observations on these 3 samples. And then there's a 1 missing value that you do not observe, then can you really infer from these samples the value of this last one, right? Can you infer that in a clever way? Is it really possible to do that, right? How will you predict that? If you predict it as 1, means you predict it as this red, it seems that you are reasonable. For example, you just have one line to cut these two stuff. You say, okay, it's 1. But if you kind of say it's 0 because there's some symmetries, right, it's also reasonable. And yeah, that's also an argument, right? So, and then the no free lunch theorem tells you, okay, this kind of question should not really be asked if you do not if you consider a function space with no prior knowledge. That means all these possible targets are equally likely as your target. And then that means it is equally likely this being 1 or 0. It means even a random guess. For example, it is, the name here is called blind search. The blind search means that for any position you did not observe, you randomly pick a value for that. And there's no algorithm that can beat this kind of random assignment of these values. So that is a no free lunch theorem. Therefore, we shouldn't compete for who is more smart in these problems of inference. No, that is not possible. All you need to understand is that problem kind of evenly distributed through this hypothesis space? Do we have prior knowledge about that space? For example, we have understanding that this space, like has higher regularity. That means, okay, you observe these two, this one is likely red, right? That is with the information of regularity. Regularity is usually the basic prior knowledge we have for many AI for science problems. Yeah, we don't have more structural prior, but we do understand its regularity. Therefore, the regularity can help us like narrow down a very specific kind of predictions that are usually more likely to be the ground truth. Okay, so no free lunch theorem is really important. Yeah, so you shouldn't, whatever the algorithm you see always kind of very nice proofs, you always should have that no free lunch theorem in your mind. You ask the following question: is it really a free lunch? Yeah, so what is its lunch? You must ask that question. For example, you kind of write down for example, a revised version of the pins, right? You have specific designs, and then you must ask the following question: is it a free lunch? Right? If not, what is its lunch? What kind of characteristics of the problem that can benefit from your design? If you did not say that clearly, then this paper does not really get any information. I can coin 1,000 different kinds of algorithms. And after reading all this, none of them can actually work for your problem, right? Because these algorithms do not provide you any insight about their lunch, right? So that problem, what is a lunch for that algorithm is really, really a very, very important problem in your research, I'd say, particularly in AI for science. Okay, and now there's still some facts probably you should know, and probably you will see these words in this deep learning theory research. There are different aspects with respect to problems in this deep learning theory, and there are like generalization, optimization, approximation, robustness, interpretability, and you may constantly encounter some of these. And generally, there could be like, on each of these topics, there could be tons of papers that try to tell you something about that. And there's some cautions I must tell you that in the neural network, so these are different aspects. I use the word of aspects. These are different aspects of the same algorithm. Yeah, you should never, if you, for example, you are an optimization person, if you only look at this neural network from the optimization perspective, that will not lead you to anywhere. Because that's the same thing, right? For example, there's a person there, right? So it has different kind of aspects of that person. They are from the same thing. They are not completely different stuff. If you only look at the generalization and without realizing that it is realized through some optimization procedure, or realize that there's a model that with certain approximation capability that you care about, then you miss the important part of what you are looking at. Okay, and later, since our topic focus on the generalization, because there's a reason that generalization is the most important aspect of this deep learning, because we definitely don't really want a model that can only predict on these training samples, right? We bet on this generalization capability. And therefore, understanding its generalization capability is kind of the most important part, but it is closely related to all different other aspects of the problem. I will first tell you about what are the problems or phenomena we observe regarding these kind of aspects other than the generalization. First, it's about optimization. So the optimization part, there's a very kind of important phenomenon that despite strongly non-convex loss landscape, gradient-based training of large neural networks often find global minima. So that is a very kind of a very strong phenomenon we observe with some understanding, but not a complete understanding. So, but this phenomena, the observation of this phenomenon tells you, okay, we used to feel, okay, there's a non-convex loss landscape. It are likely look like this with lots of local minima, right? And the global minima can be difficult to find through some local learning algorithm. That is our understanding of gradient or greedy methods, right? It can be trapped. However, this phenomenon tells us that this picture is actually wrong. Okay, please.
Sorry, I think
Yeah.
so. How do you even know?
Oh.
So how can you claim that?
Okay, so generally what we do, first of all, so it's all these phenomena are not formulated in mathematics. Means that its strength is that we have some setups. For example, in the image classification problems, we ask the following: is it easy to get to 100% accuracy solution regarding the training samples using large networks? The answer is yes. Yeah, and also, like language model is a little bit different because there are kind of situations where the right words can be like different. Therefore, the global minima is not kind of a zero loss or any kind of accuracy stuff. But there are other kind of regression problems. We can observe the tendency that as you can plot the log-log graph and see there's a tendency that it goes to zero if you use a large enough neural network. But you see that there's often, like this often, words often. It's a kind of vague, but still we observe it. And also if you are doing AI for science problems, yeah, often you don't worry about that, right? That's the strength. Yeah, so I don't say it's a kind of a conclusion, but it's an important observation. Yeah.
So when we
Right.
and you will only
Right.
so
So the gradient descent, that statement for the gradient descent is definitely true. It's just that there's not many local minima. Yeah, so the loss landscape. So this loss landscape, if you plot in this way, it suggests lots of local minima, right? But actually, that's not true.
Again, I disagree with that statement.
Yeah.
Very close to the global law.
Yeah, what you are saying is that actually this, this argument has been made using these split glass models in like 2015 or 16. However, that picture is wrong. Yeah, I can tell you there are reasons that, that the conclusion in that model, meaning that there's a lot of local minima that are close to global, almost a global minima. That is not true. And also later, in my later talk, I will tell you exactly how that looks. And it is not like there's a kind of isolated local mean. No, there's a kind of, the critical points are mostly like the degenerate, these manifolds. It's not like isolated points. And yeah, so, and, but your questions remind us the difficulties of like talking about this phenomenon, because like this word often, right? It's really kind of vague. But still, if I kind of, without all this practice, right? You do not practice. I just tell you, okay, it is a non-convex problem. We use gradient descent. You worry a lot. However, but with a lot of this experience, you worry less. That's just the description of that. Yeah. Oh, what's the meaning of large? That means if you trapped at some local minima with a small size of network, then you increase the size of network. That helps. Yeah, that's the meaning. Because we can coin up these a lot of examples where it indeed has local minima. Yeah, it's easy to do that. But there's a tendency that if you increase the size of the network, these local minima can disappear. Yeah, there's a lot of details to that. Yeah, that is also the difficulty of this problem. And then we can ask, if there's this kind of general thing we observe, what is the geometry of the loss landscape that is better than what we used to kind of have the picture? Okay, that is optimization. And regarding the approximation, so what we observe, still, it's a kind, you can say it's kind of both, but some architectures are more parameter efficient than others regarding particular class of tasks. And in that, what I mean, why I always emphasize on the particular class of tasks, although we did not really prove theorem like no free lunch theorem, but still you can think that each of these architecture or model may have some targets that may benefit from that design, right? It is not necessary that all targets benefit from this, the approximation of specific architecture. Yeah. For an image like the CNN, we know CNN is superior to this fully connected network, and the transformers are kind of much better than the LSTM method from this experience of OpenAI. And the problem is how to quantify the difference in parameter efficiency between architectures, because we constantly observe that certain architectures are far better than others in particular problem. How can we really kind of have a theoretical arguments about why that can be true, or what kind of characteristics of the problem that are particularly suitable for certain architecture, right? For example, transformer. We don't really have a good understanding of that. Okay. So, and then robustness. So the phenomenon is that the output of well-trained deep neural networks are often susceptible to tiny adversarial perturbation. So the meaning is that we use neural network to train on this image net problem, and the generalization can be very, very good till now. However, if you kind of design certain kind of tiny adversarial perturbations, and then this perturbation adds up to this image, can you tell the difference between these two pandas? I bet almost no. However, it recognized as gibbon with 99.3 confidence. Yeah, and this is a very general phenomenon. Yeah, it not only exists in this image recognition problem, but also exists in large language models, right? But large language models is a little bit better in a sense that the input space, if you only consider this kind of a space of characters, is more discrete than this image space. Yeah, but still, it is susceptible to tiny perturbations, well-designed tiny perturbations. Then in the large language model, how do you feel that? Someone will tell you, okay, you just kind of give some different irrelevant context to your problem. And then many times it can give you the wrong answer, right? But if you do not kind of give this irrelevant context, then probably it works well, okay? So, but there's this very general phenomenon that it's not so robust. And people may have the argument that because the statistics of this natural data are on a lower dimensional space, therefore, all your training and test is at that lower dimensional space. But if you perturb, you have a perturbation orthogonal to that manifold, then it suffers, right? That is someone will explain in that way, but still, whether that explanation is good enough or is it really possible? Is there an explanation that can help us improve robustness in a fundamental way? Still, that's a huge problem. And still, this robustness issue is something we can hardly solve till now. Okay, there's an interpretability issue. So what we observe is that one can hardly obtain an explanation with prediction power. So what does it mean? For example, in the imaging recognition task, we have lots of methods trying to understand how this network recognizes this specific type of dog, right? And we have some methods that give you this heat map. What it suggests is that, okay, the algorithm pays attention to, you see, these kind of areas, right? These kind of highlighted areas. That is how the neural network recognizes this as a dog. However, if we really test the prediction power of that kind of explanation, right? It's recognize a dog based on this kind of highlighted regime. How we test? We try to perturb on the region where it does not highlight. We call it like background regime. If we do a tiny perturbation on the background regime, does it change the prediction? Or is it more robust to the perturbation in this background regime? The answer is no, it is not robust. This is an example where I only add the perturbations on this kind of background, and I think you may not really see the change. The background, even the background is a very tiny change. However, the prediction becomes different. Oh, so this is the correct prediction, and this is the kind of a new prediction after the perturbation. So, yeah, so I also don't see the difference, but the neural network predict a new category. I don't know what is that, but it's a new category. It's not the original category. Yeah, so it's very easy to do this kind of task and reproduce this result. Therefore, you can have a seemingly understandable explanation or interpretation of the model. And however, if you ask whether we can bet on this prediction or bet on this explanation to really predict things, and the answer is generally no. Okay, and then the problem is, when is it possible to obtain explanations with prediction power? Yeah, it is perfectly possible that some of networks, particularly if the networks just overfit all the training data, you cannot really have a good explanation of why the neural network predict, for example, a dog, because it just overfits the training data, right? But in which sense this explanation, strong explanation is possible, that's still an unsolved problem. Okay, and now, so let's come to this generalization puzzle. So this, I skip the generalization because I'm going to emphasize on the generalization in this part. Okay, the generalization is the most important aspect of this problem. So, yeah, most of you have seen the slides on the workshop, and we are using these learning systems with increasingly large size, and with like the DeepSeek, like 600 billion, and the recent models, the leak is like there's more parameters to that. We are using these models. And it used to be the case where we are really worried about using large models. And for example, the quote from the famous John von Neumann is that with 4 parameters, you can fit an elephant to a curve. With 5, you can make him wiggle his trunk. What he's saying is that if you explain a phenomena using a model with many degrees of freedom, you can kind of fit even a kind of artifacts well, right? So the model, you fit it well, however, it does not mean there's any reason you should trust on that. And there's also this, in the statistical learning theory, there's a trade-off they call bias variance trade-off that tells you, okay, as you increase the model complexity, and then the training error will gradually go down. However, the prediction error, the testing error, will first go down and then go up. When you kind of reach a 100% accuracy in training accuracy, you are doomed to overfit the data. So that is a general notion there. The understanding is that the complex models easily overfit. Yeah, so basically what it does is the very important factor here is the size of the hypothesis space, right? When you say, okay, how much information is contained in the training samples, you must first tell us how large your hypothesis space is, what's the dimension of that, right? And in that sense, there's like in statistical learning theory, it says that the estimation of this testing error is bounded by the complexity factor of the hypothesis space divided by square root of the number of samples, right? You get more samples, always better, but there's a factor of the regarding the complexity of the space. But that is in that framework, you get some result. How to avoid? So the general strategy is here. So you just stop here. You don't use very complex models. You must have a good trade-off. Oh, so how do you know? So it used to be the case where you should try, like, for example, different size in practice, and then to see whether it goes up. Once you see it goes up, you stop there. And that is how people do it. There are also some kind of archaic information criteria or that helps you determine, like, for example, in the kind of time series, in the linear regression of time series, and then how many terms you should consider. So that's a kind of well-posed part. And yeah, but that's not really related to the deep neural network. And nevertheless, so there's also kind of other justifications that tells you, okay, larger complexity leads to a large generalization gap or make it more easily overfitting. And there's also this outcome reader principle. It's not a mathematical theorem. However, that principle is very influential in science and in modeling community. And it tells you that entities should not be multiplied unnecessarily. Yeah, and you can see that kind of bias dominates the modeling community for a long time. And then it comes a mystery that the over-parameterized neural network often generalize well. That is proposed by Leo Breeman. And what is interesting is that it already in 1995, it says our fields would be better off with far fewer theorems, less emphasis on fetish stuff, and much more scientific inquiry and engineering. Yeah, but the later requires real thinking. I think he's he really have a vision for this field. However, few people really adhere to his lessons. And the question is, why don't heavily parameterized neural network overfit the data? He put it as a first question we must consider, because at the 90s, already there's a bunch of papers or research on this deep neural network. However, less of them really address these key questions. Yeah, that is what Leo Breeman feels. It is in contradiction with that, because when you over-parameterize, we know that you can get very low training error. And then in this graph, you are doomed to have large testing error. So that is what it says. Oh, this says that why don't heavily parameterize? Because what we observe is that even the neural network has a training error in this regime, the testing error is also low. That is what we observe. The testing error is still very, very low. So that is opted to this prediction of very large testing error. Therefore, the Leo Breeman posed this problem. Why don't it overfit? Because it's complex enough, right? We know that it can achieve even zero kind of training error in regression. However, why the testing error is still low? Right, he can't really understand. And okay, there's a modern verification to this generalization mystery in 2017 that is very, very influential paper. After 2017, we feel that it's going to the real modern kind of effort of deep learning theory research that is from this paper. So that's very important. What it says is, the title is Understanding Deep Learning Requires Rethinking Generalization. He do a kind of experiment on this relatively large data set and large kind of inception architecture with a kind of million of parameters. And then it says, okay, sometimes people may believe some kind of regularization like weight decay or this randomness crop, this kind of regularization may help the neural network to achieve generalization. However, the comparison is no, it does not really help you. Okay, this is yes and no, yes and no. However, the training accuracy, both are 100%. The testing error, the testing accuracy, no matter yes or no, are good. Yeah, therefore, it tells you, okay, these kind of regularization techniques are not key to its good generalization performance. Yeah, so it's still this. And if we ask whether it's really so complicated, it's a network really so expressive, it do the following experiment just to use random labels. It tells you, okay, for the random labels, it's always easy to achieve 100% accuracy. It means that it has the power to fit random things. Still, okay, with so much expressive power, it does not overfit. And the last slide here is about this generalization mystery in 1D interpolation. That is closely related to the numerical analysis we learned. And you can see that when we have this kind of equal space samples, and then we try to use some polynomials to fit each data point perfectly. However, the Runge's phenomenon tells you, okay, you could, for a certain target, you could end up with these oscillatory fittings. Yeah. And then that definitely overfits the target. And there are different strategies of, for example, splines or that, but there's a traditional wisdom that probably if you lower the degrees of these polynomials, though you do not capture each point exactly, still you got some train, you can avoid this kind of overfitting or this unbounded oscillation. And however, there's a modern wisdom suggested by neural network that we just use a neural network with this parameter size much larger than the size of the samples. For example, this is a very early experiment by Lei Wu, Zhang Zhu, and Wei Nan Yi in 2017. It tells you that, okay, we just have these 5 dots to interpolate. We use this kind of neural networks of different layers, all with parameters over 1,000. And then you can see these solid curves are what the neural network actually learned. And you see there's a reference, this dotted curve. This curve, what I want to say here is that this dotted curve can be easily expressed by all these neural networks. However, these neural networks do not really learn this kind of oscillatory interpolation of the problem. That is what you observe. And so that generalization